Shantanu, do you want to introduce him?
Me?
I don't know.
I mean, you're this student, people like you.
No, Shantanu knows him. You can say so.
That is Nancy, that is the introduction. And it was close, but going to filter.
Has he done it wrong?
No, not at this.
Okay. Carry on because we are learning truth about 1 minute.
Okay. Okay, so great.
Yeah.
Okay, good morning, everyone, and welcome to this latest edition of Quantum Meets. It's a pleasure to introduce Soumyabrata Hazra, who's a PhD student here at QSVT. So Somo has done his master's from SN Bose Center for Basic Sciences in Kolkata and joined IIIT 3 years back. He's been working with me and he's going to talk about our joint work on some new techniques for quantum singular value transformation. So the floor is yours.
Thank you, Shantanu, for the introduction. So I'll be talking about quantum singular transformation without using block encodings, which is based on this paper. And this is joint work with Shantanu, Tomyam, Janpin, Jinzhao, and Richardson. So let me begin. So these are the topics that I will be talking about today. I will give an introduction to quantum singular value transformation.
Take that sound to be there. Otherwise, it will not
It will take me a second to attach this because it's USB-C. This is USB.
Okay.
Why don't you carry on and then once it's done, I'll let you know.
Yeah, okay. Yeah, so these are the topics that I will be talking about. I will give an introduction to quantum singular value transformation. Then we will talk about a recent technique for generalized quantum signal processing. Then we will talk about some Hamiltonian simulation methods like Trotterization and some classical extrapolation techniques. Then we'll look into some applications of our method, the algorithm that we propose. Then we'll introduce another randomized QSVT algorithm. Yeah. Then we'll introduce another randomized QSVT algorithm. And we'll see some lower bound proofs for Hamiltonian simulation, lower bounds like in the depth of the circuit required to simulate a Hamiltonian in randomized technique. And then we'll end up with some open source code. Now, so what is quantum singular value transformation? So you can say that it's a mathematical framework that encapsulates major quantum algorithms, which you know like Hamiltonian simulation, solving a quantum linear system, Grover search, phase estimation, even like factor. So what it does is that, let's say you have been given an operator A, which in general can be non-unitary, and you want to apply a polynomial transformation to the singular values of that operator. Now, in general, because A can be non-unitary, but in the circuit model of quantum computation, we always deal with unitary matrices. So that's why we introduce this concept of block encoding, which gives you a method to access this non-unitary matrix via a bigger unitary. We say that this matrix, this non-unitary A matrix, is encoded in the top left block of your unitary. So this is called block encoding of A. So U block encodes A. And the job of QSVT is to apply a polynomial transformation to this matrix A, to the singular values of this matrix A. And you will end up getting a matrix that looks like f of A, and the other components that you don't worry about, we have just denoted it by star. So now, let's say you want to simulate Hamiltonian simulation. For that, f of A, like f of x, this function will look like e to the power ix. Let's say you want to do matrix inversion, or like you solve quantum linear system, in that case, this function f of x will look like x inverse. You want to do Grover search. In that case, you have to implement a polynomial that approximates these functions, which is like theta of x, like a step function. So from this point of view, yeah. So we'll look how to build this unitary A. For now, we just assume that if you have the description of A, then we will see how to build U from A. Then we'll look into different techniques. You know the description of A. It can be a linear combination of Pauli's, some linear combination of unitaries in that sense.
What are examples in which we cannot frame it as USB? What are examples in which we cannot frame it as USB?
So I have not defined what kind of functions that I can implement via QSVT. So I will define it later, that the functions that you can implement via QSVT has to have a specific degree. It has to be either even or odd. It has to be also be bounded in a specific region.
I'm asking, do you know other top like algorithm which we cannot write as specific?
Yes, there are algorithms which you cannot phrase as kind of a polynomial transformation. So there could be.
Okay.
Yeah, I mean, you would have to think. There are algorithms of the same task, some of which are very different. Think about the adiabatic algorithm.
Yeah. So from that perspective, depends on what kind of problem you want to solve. Your f of a will vary accordingly. And the job of QSVT is to implement a polynomial transformation, which polynomial will approximately implement f of a. Now, in another way, you can see this, that if you apply u to 0 psi, where 0 is an ancilla and psi has the same size as a, then you will end up in this state like 0 a psi plus some orthogonal state, which is orthogonal in the ancilla. So if you measure the ancilla and if you obtain 0, then in rest of the qubits, you will have a state which is proportional to a psi up to some normalization factor. So it's the same framework. If you write the block encoding or if you get this kind of a thing, that's the same thing. So in general, the unitarity of this matrix U enforces that the norm of A should be upper bounded by 1. Now, in general, the matrix A its norm need not be bounded by 1. It can be some arbitrary lambda which is greater than 1. In that case, you can have a block encoding of A over lambda. So before going into the circuit description, how QSVT implements this transformation from how we go from A to f of A, we'll see how to build the description of U. You have been given the description of A, how it looks like. From there, we'll see how we can construct a block encoding U. So let's say that A can be decomposed into a Pauli decomposition, which is L Pauli strings. Each pk is a Pauli string, and lambda k are coefficients. Norm of A is upper bounded by lambda. This is a special case that I have given an example just for ease of understanding. Let's say L is equal to 4. So you have 4 different Pauli strings. And this particular circuit implements the block encoding of A. So what it does is V is a unitary that is acting on the ancilla qubits. So psi is your system of interest. There are 2 ancillas here. There are 4 controlled or anti-controlled Paulis that are being acted on, P1, P2, P3, P4. In the end, there is a V dagger, and then you measure the ancilla qubits. So now in general, when you have L different Paulis, in that case, your circuit depth. So here we are considering the circuit depth in terms of how many of this controlled Paulis you are applying. So in that case, your circuit depth will scale as order of L. And the number of ancillas that you require, that scales as log L. In our paper, we have proved that this is actually a lower bound, that you at least need logL ancilla qubits to construct a block encoding from this kind of a decomposition of A. Okay.
Can you say regarding
Yeah, so this circuit implements this unitary U. Now, if you measure these two ancillas and you observe 0, you basically get a state like A psi, where A is written as lambda k pk. So this is the circuit that it scales as the number of turns you have in the decomposition, order of L, and the number of ancilla you need is log of L. So that's it. Now we'll look into how, so we have built the description of this unitary U from the description of A. So now we will see how QSVT implements this transformation, how we go from A to F of A. Yeah.
So you said you have a lower bound, right?
Yeah.
Which just to be sure was that you cannot, like you need essentially logL qubits for consideration. So is that for exactly getting this unitary, or is it also account for approximately?
No, exact.
For exact.
For approximation, we suspect that you can do better, but nothing is known. I mean, nothing was known to the exact case also, but we could prove it or not.
And can you say a little, will you say a little later about how you do it, or just
Oh no, that proof I will not
you
include.
not say? Yeah. You want to say a few words on how you prove it? Or you think it's
I think it's a little bit more mathematical.
okay? Just not off or I mean,
So it's a function, yeah.
Lower bound.
So
you
basically
need
what you consider is you consider a large class of circuits, okay, where a family of circuits which encompass these sorts of LCU kind of circuits. So LCU takes logL qubits. You find a family of circuits which encompasses LCU and show that using those kinds of circuits you cannot do better with them. So that's the idea. The key insight is to construct a family of circuits.
the relaxation.
Yeah, and then you try to take each PK and try to ensure that if you could have a block encoding of level, somehow in less number of qubits, somehow you mess up some discrimination. You could discriminate between states.
Okay, so this is a circuit that implements the f of a, the desired function. This is the general QSVT circuit. And so what kind of functions can you implement via QSVT? So it should have a specific degree D. The circuit depth will depend on what the degree is. It should be either even or odd. It should be upper bounded by 1. F of x should be upper bounded 1 for the region x in the region from -1 to 1. Degree is of a polynomial like so like f of x can be in general a function, and QSVT will implement a polynomial that approximates that function. So that polynomial will have some specific degree. So now here you will see that there are logL ancillas, which comes from the fact that just to have the construction of U, you need logL ancillas.
Function has or it cannot be neither.
No, it has to be either even or odd.
The polynomial
In this framework.
There is a restriction of it.
Yeah.
That the polynomial has to have a definite value.
Later we will see that we can relax this condition. It will work that even if it is neither even nor odd, then also it happens to be 2. We will see the circuit description for that.
What is the node and you
So it's like x square plus x to the power 4. It's like an even. And sine x, you can think it's like kind of
like what
not sine. So like f of x is equal to f of minus x. That is even. And f of minus x is minus of f of x. That is odd. So you need logL ancillas just to have the construction of U that we have shown how we can construct. And on the ancillas, we implement some phase rotations, and we apply this interchangeably. Phase rotation U, another phase rotation U dagger. So if you are implementing a polynomial of degree D, you have to implement U D by 2 number of times and U dagger D by 2 number of times. On total, you will have to imply U and U dagger total D number of times. So the higher degree of polynomial that you want to implement, the circuit depth grows longer. Okay. So now we define the circuit depth in terms of the number, how many times you are implementing U. So we are implementing U total D number of times, and each U has a depth of order L. So this circuit has a depth of L times D. Now, this works when the norm of the matrix that U block encodes, the matrix A, its norm is upper bounded by 1. Now, in general, we saw that in general the norm can be upper bounded by lambda. So in that case, the circuit gets scales by a factor of lambda. So it becomes L times D times lambda. As an example, let's say you are implementing e to the power IAT. You don't have a block encoding of A. Instead, you have a block encoding of A over lambda. So you can write e to the power IAT by e to the power A over lambda times T times lambda, which means that you are now implementing the Hamiltonian simulation for an extended time T times lambda. So it scales the degree by a factor of lambda. So in general, the circuit depth of QSVT is L times D times lambda, and the required ancilla is logL. So our goal in this paper is that we want to implement this kind of a QSVT transformation while using minimum number of ancillas and still retaining the state-of-the-art circuit depth.
What is that gate before the phase is that?
So it is a e to the power I phi z. There is a projection phi. So it's on a different qubitized basis. It's a phase gate.
So Z phi, you can think of this as a reflection. It's a single qubit reflection around this one, like here. So identity minus 2.
Yeah. 2 pi minus identity.
And the circuit does not depend on whether it's all. The circuit is the same. It only depends on the.
So if the degree
depth I'm saying the degree.
So it only depends on the depth.
Yeah.
So how many times you are applying U and U dagger? If it is like
I was asking the circuit.
No, circuit description remains the same.
So if it was, say, this is for even degree, for odd degree,
there will be one more U coming
in. One, so it might be T plus 1, but you don't really care because it's still order of.
So this is the original description of QSVT. Now, in order to do the same QSVT transformation with using less number of ancillas, we use a new concept which has been recently introduced by Mortlag and Webe. They call it generalized quantum signal processing. So, yeah.
Is there some intuition for why that the previous circuit gives you the top input?
So the U already has A in the top left corner, A, and you can show like for so it is a proof in iterative manner. Let's say you have for d equal to 0, you show that it implements a function. Then for d equal to 1, you implement one more U dagger, and so that also if d equal to 0 is satisfied, d equal to 1 also from there. From there you can like kind of approximate these kind of functions. It just has to be satisfied these three constants. It has to be bounded, even or odd, and
so I guess the intuition, is that one when U has the block encoded A, right? And these are single qubit rotations, right? So what these sequence of single qubit rotations does is that it divides the whole space of A into a direct sum of its eigenvectors. And then if you carefully choose these angles, phi, what you do is you implement independently in each of these subspaces that you work here, the function, the polynomial, P of lambda 1, P of lambda. So you choose these phi's carefully so that you, in this direct sum structure, you implement these.
And these files don't depend on.
It depends.
Files depend on the.
Yes. So so there exists a classical algorithm, efficient, extremely log, which you can run.
Even the profession of the
polynomial, so it gives you the.
Yeah, sorry.
Yeah. Just to understand the circuit, you are applying the e to the I phi to Z phi, and that is the sandwich between this change of basis.
Yeah.
And then again you will implement U and then
interchangeably U dagger, then U dagger again. And in between U and U dagger, there will be this phase operation.
So would it be okay to just use U once in the beginning and then U dagger again?
No, that just means that you are implementing only one phase gate. Like you can just add it to phi 1 plus phi 2 plus phi 3.
So after U dagger, what will come?
Then again U will come, again a phi, then again a U, and again a phi U dagger. So on total, you have applications of U d by 2 number of times when d and u dagger will be 2 by 2 number.
Unitary.
USD unitary.
But the first 4 gates, I think, repeat, right?
Yeah. So you just repeat it interchangeably.
First 4 gates.
You have to put
Yeah. So on total, u and u dagger will total, you have to implement total d number of times if you are implementing a function, a polynomial of degree d. So now, in this circuit they introduced recently, which is called generalized quantum signal processing. This also looks very similar to QSVT. The change is that you have only one ancilla here, and the phase gate has been replaced by RJ. Where RJ you can think as like arbitrary SU2 rotations. We are not only implementing the phase e to the power I5z, it can be arbitrary SU2 rotations. And we have replaced the unitary U by UGQSP. So UGQSP has a specific structure, like it encodes e to the power IA in the top left block. Earlier we have U, which was encoding A in the top left block. Here we have a specific structure like e to the power I.
also have to have the octagonal terms 0 and
0, 0 and identity. Yeah.
so that's a stronger restriction than just a stuff.
We will later see how we can construct, how we can implement this particular UGQSP.
And just to be sure that the U itself requires some log L in the qubits, right?
So in this case, that
And here, how many ancillas do you need?
here, like you only need one ancilla here.
So for implementing UG.
For implementing UGQSP also, you're like you will need only one ancilla.
So if you assume, so there you assume an oracle, okay, which is U. Okay. Suppose you have a block encoding of Q, then you needed one extra for Q. Yeah, okay? But to construct the block encoding of U itself, you needed that.
That's what I was asking.
Here, the oracle that you assume access to is e to the IA. Right? Now, given that oracle, you can construct UGQSP just by adding another answer. And the question is, how do you get e to the IA?
Yeah.
So then you would need many ancillars.
Yeah.
So it's not clear that it's unequivocally better than what we have.
No, it's not. So that is where our
Yeah, so here we just assume that you have access to this kind of unitary. We'll see how we can implement this UGQSP via using some better methods. And so this circuit implements a polynomial transformation of e to the power I. Earlier we were implementing some function f of a. Here we are ending up implementing p of e to the power I. And this polynomial has less restrictions in the sense that this particular polynomial, which is called Laurent polynomial, it need not be either even or odd. The earlier other two restrictions remains the same. It used to have a specific degree d. Just could also be bounded by 1 for z being in the complex unit circle, but it need not be even or odd. So that condition is relaxed because of the introduction of this arbitrary SU2 rotation, single qubit, and this particular structure.
Okay, the output of this circuit is going to be a block encoding of
P of e to the power I. It's a polynomial transformation. So if we can show that this P of e to the power I is equal to f of a, which we were earlier implementing f of a, if we can show that f of a is equal to P of e to the power I, then basically we are done. Our goal was to implement this f of a.
And I'm working the definition of this Laurent polynomial. Sorry, I don't.
So it differs from the general polynomial by that it can have a negative degree also.
So the
And it is defined on the complex plane. Yeah.
The powers can be positive or negative, and this is a Laurent polynomial in e to the ix. So that is why it's in the complex.
Yeah. Like P of z can be a complex number, and it is bounded in the region for unit circle in the complex plane. Okay. So now, so this unitary that we explained, that UGQSP, you can see that you can write it in this form of exponential of I times some Hamiltonian, this kind of form. So this essentially says that you can implement this unitary using any Hamiltonian simulation technique, because you can write it in the form of e to the power I times some exponential, some which you can refer to as Hamiltonian. You can implement UGQSP using some Hamiltonian simulation technique. So here we will use general Trotterization method, which I will explain later what Trotterization is. But this is a summary. Trotterization is basically a Hamiltonian simulation method that implements e to the power IHT up to some error epsilon, and it has a circuit depth like lambda t to the power 1 plus some small constant and epsilon to the power some small constant. So if you are using the higher order, more higher order in the Trotterization, then you will be implementing a more closer approximation to the actual Hamiltonian evolution operator variety.
So in the previous slide, if you only had an approximation.
Yeah.
So if you only had an approximation for QSVT, the results still hold with some small error. So they don't show it in their paper. Also, you have to do it.
Yeah. So in general, if Hamiltonian has this kind of a decomposition like lambda k H k, Trotterization implements a Hamiltonian evolution up to some error using this kind of a circuit. So what we say that we replace this UGQSP by Trotterization techniques. Okay. So now we can define our problem as like, let's say you have a Hermitian operator A, which has a de Pauli decomposition times lambda k pk, and it has L terms, and its norm is upper bounded by lambda. And the goal is to estimate. So by the end of this GQSP circuit, you measure some observable and you see some outcome. So the goal is to estimate f of A acting on psi naught, where psi naught you can say that psi naught is acting on the initial psi is replaced by psi naught. Then your goal is to estimate this quantity, which is very similar to the expectation value of the observable O in a state f of A acting on psi naught, except there is the normalization factor. So you can also include that here by using amplitude amplification techniques. But this is just for simplification that our goal is to estimate this. So now what we do, we use the same GQSP circuit, replace the UGQSP by a Trotterization, some piece order Trotterization, and we can show that this method, that which we call QSVT with Trotterization, it uses only one ancilla, and the circuit depth is very much close to the actual QSVT, which we already showed why it comes to be L times D times lambda. And here it comes to be L times D lambda plus to the power 1 plus some small constant. And the classical repetition is 1 over epsilon square that remains intact because of the Hoeffding inequality. Okay. So the improvement that we have done is that we do not need logL ancillas, we do not need block encoding. We just use Trotterization, which is a standard technique in Hamiltonian simulation. And we need only one ancilla to do this. And the depth remains almost the same. And in the end, we use some classical extrapolation technique, which I will again explain later why we use that. So these are the three techniques that has been combined, like generalized quantum signal processing, higher order trotter, and classical extrapolation.
So maybe you would want to motivate why you would want to do classical.
That I will explain later. So this is a more generalized version of the algorithm, which we call an interleaved sequence of unitaries and Hamiltonian evolution. So now consider you have D different Hamiltonians, H superscript J going from 1 to D. And each Hamiltonian evolution, between each Hamiltonian evolution, there is a arbitrary unitary line, which we call Vi. And you apply this total D number of times, this Hamiltonian evolution. And in between, there is a Vi or Vj something. So you call this whole unitary W. In the end, you start with psi naught. In the end, you measure some observable O. So the goal is to estimate the expectation value of the observable in the state W acted on psi naught up to some error epsilon times 1. So this is a very unique algorithm which was not existed before, and we'll show that QSVT comes to be a specific case of this particular framework. So in this work, we saw that here we also don't need any ancilla. This e to the power I, this Hamiltonian evolution, you can just replace it by Trotterization techniques. And the depth remains the same as the earlier QSVT, L times D lambda to the power some constant. And the classical repetitions is also the same because of the Hoeffding inequality that does not change anywhere. So we are using two techniques here. We're replacing the Hamiltonian evolution by Trotterization, and then in the end, we are using some classical extrapolation. Now, this task encapsulates QSVT in the sense that if you consider the different Hamiltonian evolutions as like the same Hamiltonian, let's say H superscript 1 up to H superscript, they are the same Hamiltonian H. So in that case, this circuit is basically same as this one. In the UGQSP, you have Hamiltonian evolution. So R1 times identity that you replace by V naught here. Each Rj, that was the AC2 unitaries, you replace it by V0, V1, V2. So QSVT comes to a specific case of this algorithm. Similarly, also, you can do time-dependent Hamiltonian evolution in the sense that, let's say your Hamiltonian is getting fixed from time t equal to 0 to t equal to 1. Your Hamiltonian is fixed at H1. From t equal to 1 to t equal to 2, it is fixed at H2. So that total evolution from 0 to t, you can implement it by discretizing that Hamiltonian evolution, and you can consider that V0 to Vi, all these are identity.
So the previous point you mentioned,
so you replace all these different Hamiltonian evolutions by the same Hamiltonian, and V0, Vi, these are the same
you have ancillas, right? And you don't have ancillas. How you handle it?
So we don't require ancillas anywhere here.
So you are considering V to be R times identity.
V to be R times V in the other slide.
Yeah. And then this UGQSP would be this e to the IA tensor.
So yeah. So basically you can disregard the ancilla.
Yeah. So basically, so
It is right on the bottom. It would be easier.
Yeah,
Just clarify how you see that as a special case on the board.
just wait for the first couple of
Yeah, sorry, I know it's a dumb question, but just so
like just wait for V0 and E to the power I.
yeah, I'm just very curious to see how the ancilla is removed. No, the ancilla isn't removed.
It is in
But in
V0.
this circuit, there is no ancilla.
yeah. So but psi 0 would be an n+1 qubit state, right? Instead of an n qubit.
So your mapping for the initial state can change.
Yeah. So essentially,
That is
yes.
abuse of notation.
Yeah.
So,
then it's
so V0 can be R times
I was still very concerned about ancillas, and so you could be very
No,
careful.
that would have been clear if I had mentioned the number of qubits in the psi 0 itself. That would have been better.
But then it's
So this is a general framework, right? Like psi 0 could be anything,
not it got. I think I just got confused with the notation. Okay.
Okay, kind of just go to the previous one.
No, but then you also
The previous picture. Here, let's say if R1 is of the same size as the unitary, you are in the signal processing unitary. Then
R1 is of the same size as
no, so R1 has to be smaller than
R1 is
So it is only acting on the ancillas.
just so you are using the fact that in that case, like the number of inputs for both, like unitary and Hamiltonian is kind of same, right? So that's why you don't require ancilla.
you repeat again.
So in that, in the single picture, like whatever it is, the number of input qubits, it seemed like the one that the same number of qubits.
go to that slide, like the general framework slide. So
Yeah.
I mean this, but you can split it up. You can add identity somewhere. Let's say you can make V0 to be some small unitary tensor identity. Then
Yeah, wouldn't have the ancilla. Whatever identity that one wouldn't have
Yeah, so-
ancilla.
so depends on the other one, right? E to the IH, right? If E to the IH requires say n qubits, whereas V0 works on L qubits, while on n minus L qubits it's identity. Then you don't have any answer.
Okay, that is not called ancilla.
No. Ancilla is
No, ancilla is something that you require.
is say n qubit. Whatever extra unit is there.
Yeah. So
No, I'll ask it. I think.
No, but I can clarify on the board.
Because like your function ancilla is here as well, and
No, wait.
yeah, if you use the same size 0, you can maybe size 0 prime. The jobs here are horrible, but okay, I can get some from.
So in GQS, so let's look at this framework, right? So you have some psi 0. This is say V0. Then you have e power I h of 1 and v1 and so on, right? Right? Now let me say that v0 is some R0 tensor identity. This acts on a single qubit, this acts on n qubits. Right? So here what we are saying is that this is a circuit. Here, this is some initial state.
But
You don't
why don't you write down the dimension of the initial state as well?
This is general, right?
Yeah.
So if this is, let's say this is a dimension q, or say q qubit state, right? Right. Let's say this is a q qubit state, right? This is a q qubits. This is q qubits.
Yeah, everything is equal with after that. Yeah, yeah.
Right? Now let's say q is n plus 1. Okay. This is one single qubit. This is n qubits. This is how v0 is described. Let's say you describe e to the, so let's set h of j equal to 8 for all j. Right? And define, okay. It's just a no, this is comma. Yeah. This is some h tilde. Define e to the I h tilde as e to the I, or rather just say h tilde is h tensor identity, or identity tensor h rather. This is I2 tensor h, where h is of n qubits again. Right? So then you have, this is a special case of this, because
But the ancilla count is
ancilla count is 1.
no, that's ancilla count is 1, yeah.
Because now your input space, so you again set psi 0. So we some
0
identity 2 tensor psi 0 tilde.
Right. I mean,
Right.
it has to be a state. Like, the first thing has to be a state, not
Yeah, I mean,
Like 0, fine. 0. Yeah.
no, just 0.
Yeah,
Yeah,
that's
it's 0. Sorry.
Yeah,
It's
no,
fine.
Huh? Yeah, that's what I was asking. That like it looks like the number of ancillas in that circuit, and now in your circuit is the same. That's what I was.
Yeah, so so the number of ancillas there is 1.
Yeah.
In our circuit, it's 1.
Right.
Right? If you consider GQSP using our framework, then again the number of ancillas would be 1.
Right.
The difference is this e power ia. There they need oracular access. So if you want to construct e to the ia from A,
You need further ancillas.
yeah, you need like Soumya was like,
logL ancilla from there.
and you basically end up in the same place. You start from a block encoding of A, you end up in a block encoding of e power ia. Then you end up in a block encoding of P of e power ia. Whereas here you just replace everything by Trotter, and then do extrapolation to have near optimal like dependency on the depth and the precision.
yes, so you don't have benefit over ancilla. You don't have benefit over ancilla, you have benefit over.
No, we have benefit over ancilla. If you consider the end-to-end algorithm here,
Okay, end-to-end.
if you consider, so here it's yeah. So even standard even standard QSVT assumes access to this, right? Like Soumya was mentioned.
Sure. And this itself requires log.
This requires logL. If you just give me this, give this to me as a black box, then in standard QSVT also I need one ancilla. But if you want to run it in practice, if this is say a physical Hamiltonian, right, of local terms, let's say L local terms, then you would need logL ancillas to just get this. Same here.
Thank you. That helps. Shoot, I forgot to point the camera.
It's fine.
You can move on.
Yeah.
You mind your slides.
So I have defined the problem statement, and so I have also defined this. I have also introduced this. So this is a very general framework, as we have said, and QSVT is a particular case of this. Also, you can think of time-dependent Hamiltonian evolutions. And
the classical extra.
That I will explain. I will come to that. I'm coming to that in the next slide. Yeah. So what is Trotterization with extrapolation? So Trotterization, as we have said, that it is a method to implement the Hamiltonian evolution like e to the power IHT. And extrapolation is a classical technique that you can do as a post-processing in your classical computers. So let's say that your Hamiltonian has a decomposition in the terms of like sum over j hj, such that e to the power I hjt is easily implementable. Okay. And the norm of h is, let's say, upper bounded by lambda. The goal is to estimate expression of an observable O in a time evolved state. For you are evolving with respect to the Hamiltonian H for time capital T, and you want to estimate the expectation value of the observable O in this state. So the first order Trotterization, it implements gates like e to the power I sometime h. You are implementing those easy to implement unitaries for a time step size s times t. You repeat this for all the Hamiltonians h1 to hj, like the whatever the limit of the j is. Then the whole block you repeat that 1 over s number of times. So in total, you're running the Hamiltonian equation for time capital T. So this is for the first order Trotterization. The more higher order you go, the more closer approximation you get to the original evolution e to the power I h. Like if you are implementing a pth order formula, then you will be approximately implementing, the error will be like t to the power p plus 1 of the order of t to the p plus 1. So now why extrapolation do we use? If you take limit s tends to 0 for this formula, for this first order Trottle formula, that will be exactly equal to e to the power I h. But in practice, you can never implement Hamiltonian evolution. You will always implement Hamiltonian evolution for a finite step size. Is equal to S1 or like S2, S3, S2, something like that. So you have a circuit description like this: product of j e to the power I st of hj repeated over one, the whole thing repeated for 1 over s number of times on the initial state signer. Then you measure the observable O. We have a circuit description for this quantity, the lower quantity, which will be exactly equal to the original estimation in the limit s tends to 0. But in practice, we will always be implementing, we'll always be getting approximating this particular quantity for some finite step size s equal to s1 to s2, s3, something like that. Classical extrapolation is a technique that helps you to approximate what the value of this quantity should be at the limit s equal to 0 using the values at finite step sizes. The more number of samples that you use in the Trotterization step size, the more accurate you can get what the value of this function should be at the limit s equal to 0.
What changes in higher order Trotterization?
So in higher order Trotterization, the like you implement like the circuit description like this. This formula changes to a more complicated formula, and you can implement like a more closer approximation, like the error with the original Hamiltonian evolution will be of the order of t to the power p plus 1. If you are implementing pth order formula, the error will be t to the power p plus 1.
So you can think of it like this. So if your h is a sum of local terms like he has written, so these local terms may not commute among themselves, right? So e to the iht will not be, say, just the product of the individual term, right? Because there are these commutators which will come. So now how do you get e to the ih in terms of these local? Now there are different ways. The most basic approximation that you can do is that, right? Where you just take the basic formula of the product of local terms, just that you do it then for a very small step size so that the error introduced is there, and then you keep on repeating. But there are more complicated formulas for e to the iht. Okay, these are called Suzuki, by Suzuki actually, so that's why they are called Suzuki. And depending on how you choose, these hj's, like e to the ihjt, which order you choose them, how many times you put them, you get different orders of order. So ideally, you can have 2k order, p order.
So the second order problem will have one commutant.
It will have commutators or commutators. This already, if you look at the error between the first order Trottle like he has done and e to the iht, the error term will depend on s, right? Of course, what kind of step size you choose, And you will have to choose a step size that is proportional to the sum of the commutators of these local.
For second order, will it be like a single commutator or the
Sums of all the local terms, right? So it's going to be sum over say j comma k, hj, nested commutator hk.
Yeah, you can use that Baker-Campbell-Hausdorff formula just to get the whole series.
So even my question was that even for second order, you get nested commutator.
Yes. The error in the error.
Yeah. But the higher order you go, the error becomes the less.
The dumbest question: why don't you just go like order? It has zero error.
The circuit depth also increases. Like circuit depth also increases.
The depth is because the step size depends on your circuit depth.
So why extrapolation? So this we have seen, and this helps in reducing the circuit depth by an exponential factor for the dependency over epsilon. So in the standard Trotterization method, you have a polynomial in 1 over epsilon dependency, but a recent result by Watson and Watkins, they used Richardson extrapolation technique, which is you run the whole GQSP circuit. In the end, you do some classical post-processing, which we call extrapolation. And from that, you can show that the dependency over epsilon is exponentially improved from polynomial in 1 over epsilon to polynomial in log of 1 over epsilon. The classical representation remains the same because of the Hoeffding inequality. Now let's look at an example, which we call the ground state property estimation problem. You have been given a Hamiltonian, its eigenvalues lies in a specific spectrum. And in general, so delta is considered the spectral gap of Hamiltonian, like it's the gap between the lowest energy eigenstate and the first excited energy eigenstate. And you have been given access that phi naught is an initial state that you can easily prepare. And the ground state of this Hamiltonian H is psi naught, which is different, but it is guaranteed that phi naught has some overlap with psi naught, and the lower bound is said to be common. So the goal is to estimate some observable in the actual ground state of the Hamiltonian psi naught up to some error. Now, in general, this problem is QMA hard. If you are not given the description, if you don't know the spectral gap, or like if you cannot prepare a state which has some overlap. But if you are given that the spectral gap is this, and you can given the access to some initial state that has some overlap with the original ground state, then there are algorithms that you can use to solve this. So what do we use here? We use the same GQSP circuit, replace UGQSP by Trotterization. At the end, you perform. So there are no extrapolation techniques, like you are not repeating this many number of times. You're just implementing this once and for all. So now what kind of polynomial we have to implement here? So you can show that if you implement on the prepare phi naught, using that state function gives you a state which has some overlap with the actual ground state psi naught. And then you can use amplitude amplification. So there will be other terms here. Then you can use amplitude amplification to amplify the term, this overlap up to 1, and then use some estimation techniques. So due to that, we require some ancillas. Otherwise, in general UGQSP, as we have shown, we do not need any ancillas. And we did not need any extrapolation because we are not repeating this multiple number of times. And the time complexity remains to be almost the same up to some factor, which comes due to the Trotterization. If you are using pth order Trotter, you will be getting 1 plus 1 over p. This kind of stuff.
So is this are you moving on to the applications? You're not going to mention anything about what we do?
For
how do we use the extrapolation? Why is it non-trivial? Like
the construction of Richardson extrapolation.
No, but the point is that if you use extrapolation directly, the extrapolation that Watson and Watkins use in our framework, the error bounds don't converge.
Yeah, actually, like in this case, you can view this whole evolution as a time-dependent Hamiltonian evolution, and the construction that Watson and Watkins gave to improve this dependency over epsilon exponentially from poly in 1 over epsilon to poly log 1 over epsilon. If you directly implement it here for each Hamiltonian evolution, it will not converge like that. But instead, you can view this whole evolution, this whole circuit, like interleaved sequence of V and H. You can view this whole circuit as a time-dependent Hamiltonian evolution. It can be done. In that case, you also show that if you are implementing time-dependent Hamiltonian evolution, and in the end you are using
How do you map the time to your
we can, so that I have not shown here, you can construct a H tilde which for some specific interval is equal to V0, for other interval it is equal to next interval it is equal to H tilde. Yeah.
So it's like a Floquet-like effective Hamiltonian.
Yeah.
You can get a Floquet-like effective Hamiltonian for this whatever, like some time-dependent Hamiltonian, which is an effective, which is not really a Hamiltonian, but something that is an artifact of an analysis. You can define this as log of some whatever unitary as Hamiltonian, and then you do the extrapolation at the end, essentially. So Watson's methods were for extrapolation when you want to just implement this.
Only e to the power IH.
IH. It won't work in such general sets. So you that I was asking you to mention. Yeah. That is our key technical concept. Right. That it works in much more general sense. Right.
What are the constraints on the time-dependent Hamiltonian for which it works?
So far, what we have proven is that if you have any circuit like this,
you've done it for your family or
family.
Yeah, I thought you've done it for arbitrary.
No.
But you don't expect that to be true.
I think it is possible. So if you want, say, if you have a time-independent Hamiltonian, right? And let's say you want to do simulation of the time-dependent Hamiltonian. What you will do in the circuit model is that you will discretize that, and then you will do time-independent simulations of the discretized.
This already encapsulates this.
Yeah. You can just take B0s to be the VIs to be identity, and these H superscript J's to be these discretized. And then time-dependent Hamiltonian simulation. Special case. So instead of e to the I H superscript j, you could also have e to the I superscript j some delta t. That doesn't change anything, right? Because it just you're fiddling with the norm of H1, where we have no restriction.
So are you sketching the Watson's technique?
Yes.
Yeah, so Watson's proof, I don't know if it will work, but
I thought your proof just says that for your technique it will be good.
Yeah, but it needs to use a different sort of a method, not the Watson's methods. Directly don't do.
Right. So you have to generalize it to the time-dependent.
Yes. Yeah.
And so it works for all such families. Right?
Yes.
And then you just believe that a time-dependent Hamiltonian is a special case of this family.
This family, yes.
So therefore, you can basically get the trade-off from
yeah.
But Watson also time-dependent. Isn't that? Did you just say?
What do you mean by you can use Watson's proof? That's not Watson's proof.
No, like in generalization of
the generalization of Watson works for time-dependent.
For arbitrary. Yeah, that's what I was saying. Yeah. Sorry.
Because Watson's proof doesn't work for time-dependent.
Yeah. I mean, it's like the thing you did generally.
Yeah. So this already encapsulates many of the different techniques. That's a very general circuit. Okay. So we have more applications in terms of implementing solving linear systems of equations that we will not discuss here.
Why?
I was thinking like it is like a little bit too lengthy.
But at least the complexity, because that's remarkable and it uses like both things. Okay, fine, go on.
Okay. So this is a randomized technique. So the goal again is to implement a function like given a block encoding of A, you want to implement some function f of A, which you can approximate by some polynomial transformation. And this is a randomized QSVT that we want to do. So here there is a comparison between the original QSVT and the randomized QSVT. This is the circuit. And
what is randomized QSVT?
So I will introduce that. So this just looks the circuit. It looks exactly similar to the original QSVT. You have only one ancilla here, where you are using the same kind of phase gates. And the circuit depth, like if you want to implement the polynomial transformation of D, the circuit depth is not D here. It is little bit D times log D times some log D or log square of D. Those kind of factors are included within the depth. We call it N. So it's slightly longer circuit. But the difference is also that earlier we had block encoding of A in this form. Now here the unitaries looks like this: cos theta identity, sin theta A, sin theta dagger minus cos theta identity, which you can also give with.
You should keep these indicating for this segment. You don't have to use directly.
You can, but like A can in general be not be easy to implement. You can have like the earlier we said that H, we had a decomposition of A. You can have a decomposition of A, let's say sum over lambda j A j. And A is not easy to implement, let's say. You can easy to implement e to the power I A j t, those kind of things. So in that case, you have to again write the evolution of A in terms of e to the power I A j t, and that requires some extra ancillas.
I thought like he was.
If A is A, that also it will work.
He's going to build up a picture. This is not the full story. So what he's saying is just imagine that if A was unitary, U is of Q, right? That is a true story.
Yeah.
But it is going to be something which is going to make it non-trivial, which will probably come later. So why is it randomized? So the first thing I think you should motivate someone is what is randomized? Like why is it randomized?
Randomization will come later. I have not explained. Okay, I have not yet introduced why randomization is coming. That we'll see why we need the randomization. Because the unitary that we say, the U, the gate U that we call here is the specific cos theta sin theta in terms of that. So if A, this U is unitary only when A is unitary. But our goal was to implement polynomial transformation using QSVT for any arbitrary matrices. It need not be restricted to unitary matrices. So if U is not unitary, then this circuit will not work. So in that case, what should you do? So in that case, we say that, let's say A again have a Pauli decomposition, lambda k pk, and you replace A, you sample a Pauli according to the distribution, according to the weights lambda k. Let's say lambda k sum up to 1 here. So you replace A sin theta A dagger by pk dagger. So now because Paulis are unitaries, these UKs are unitaries. You replace the U by UK. So now this is a unitary circuit. And you repeat this many number of times. So on average, the average unitary that you implement will be lambda k pk sum over k, which exactly is equal to A. So average of UK is U. So although we are implementing this kind of circuit, which is a unitary circuit, in the end, you can implement it for arbitrary non-unitary operator A. And
in expectation
value. And earlier we are having block encoding of A in the top left. And in this case, there is a subtle difference here. We'll not have the block encoding of f of A, but we'll have a block encoding of A over some alpha, which depends on the degree. N depends on the degree as like theta tilde of t. So there is a degree scaling there. So now due to this difference, if you want to implement f of A using this randomized QSVT technique, the circuit depth will increase from theta tilde of d to d square. Because of the degree dependency is already there in the alpha, it will scale the degree, it will increase your circuit depth. So these are the crucial difference between the original version of QSVT and this randomized.
Can I add one more?
Yeah.
So the key difference between the previous setting and this setting is that in the previous setting you were given an A, which was just a linear combination of Pauli operators, and you could implement each term directly. Right? Here, what you assume, this is another setting where you assume that you can't do it directly. What you can do is you can sample each term of this description, okay, according to the weight of the coefficient, and then implement those. So this is like a sampling access model. That was a different model. This is a sampling access. And because you have sampled access, that's why it's randomized.
We are able to sample
So your
applications of the unit.
you're essentially doing this.
It's like your single answer.
The setting is similar. So the setting is similar, but here you're not, of course, implementing LCM. So here, like Shoma was saying, you have this, right? Here, what you assume is that you can sample from this ensemble, essentially. So you basically sample a J according to this weight, and that would basically correspond to a PJ. So this is like you can think of this as a different access model to what you had before.
So the other one implies this.
Not necessarily. The other one. So okay, if you're saying that this is more restricted than the other one, that's what you're saying?
Yeah, because if
Yeah,
I
sure.
like direct access,
Yeah, you could maybe
just sample it myself.
Sure. But there are the difference between that model and this model, why this is also used a lot, is because if you looked at the complexities before, it depended on the number of terms of this matrix. But if you in this setting, you can show that this disable. Yeah.
So that's the advantage of using this.
Yeah, and that's why like many algorithms use this frame.
But what is the advantage of the other one compared to this time? Because like what you're saying,
the dependence on the degree.
yes, so that one does better with the degree dependence.
So now, so how many times do you need to repeat this circuit? So as you have already seen for the previous algorithms using halting inequality, you can show that you can repeat it for 1/epsilon² number of times to estimate this quantity. Like in the end of the circuit, you measure some observable O, and you can estimate this f of A over, instead of implementing f of A, you can get f of A over alpha acting on the state side. And if you want to implement f of A, so the circuit depth scales as d². So now this for many of these randomization algorithms that implements this Hamiltonian evolution technique, this d² dependency has been earlier observed. So we also prove that the circuit depth of d² is a lower bound, that if you want to implement a Hamiltonian evolution in this sampling based method, where you can sample each term of the decomposition of the Hamiltonian with some probability, and you want to implement a polynomial transformation of degree d, then the circuit depth scales as d². So how do we do that? We show that there is a connection to the tomography problem. The tomography problem is essentially that, let's say you have been given this state ket psi, which is a linear combination of k, xk, ket k. K are some bit strings. And computing all these coefficients xk up to some error eta, it requires a sample complexity of 1/eta². This problem was earlier shown by these people. And so how do we map this? In this case, in our case, we have a Hamiltonian decomposition in terms of lambda k pk. Now let's assume that lambda k is equal to xk mod square. Now measuring this state psi, which essentially means that you will observe the element k with probability xk mod square. That essentially means that you are also sampling from a distribution where you are sampling the Pauli string pk with probability lambda k, because lambda k is essentially the same as xk mod square. And now, if you apply e to the power iht on an initial state 0, you can show that if you can apply e to the power iht using not only qDRIFT but any technique, sampling based technique, and then you measure in the computational basis at the end, then you can show, sorry, not in the computational basis, we will measure in a different basis in this case. Then you can show that you can obtain all the knowledges of lambda k. Once you get the knowledges of lambda k, then you essentially have the description of H. And then from there, you can estimate any inner product between e to the power iht psi 1 psi naught or any kind of expectation. So because this tomography problem requires 1 over eta square dependency, so it also comes here as like t square. So eta is something like proportional to 1 over eta is proportional to t here. And 1 over epsilon square again comes from the Hoeffding inequality. So on total, you repeat it 1 over epsilon square number of times. Total sample complexity is t square over epsilon square, and the circuit depth turns out to be of the order of t square. And so there are a few questions that we can impose here. So when we replaced UGQSP by Trotterization method, we did not get the exact circuit depth that was proposed by the QSVT method. We had some small constant added to it, like some 1 plus 1 over p, because of the factor in Trotterization method. So can we improve it to the exactly the QSVT depth, which was some O tilde of t, without using block encoding? Another question is that when you introduce the interleaved sequence of Hamiltonian evolution and unitary, so instead of Hamiltonian evolution, you can think that there is some quantum channel is working. So interleaved sequence of quantum channels and some unitaries. So in between each quantum channel, you discard one of the ancillas, then you again interact with the system. Can you incorporate this kind of a setting here also? And so for the lower bound, we have shown that the circuit depth scales as d square for the Hamiltonian evolution. So can it be done for general randomized quantum algorithms, not only for e to the power is?
But I think this last question has posed in a bit of a different way. So what our lower bound shows, yes, it's for e to the ixt. But what our lower bound shows is that if you want a generic technique to implement polynomial transformations in this model, you would need omega of d square. Because to implement Hamiltonian simulation, you would need omega of d square. And the polynomial that is needed to implement e to the ixt is of size t, degree t. Right? The question that you can ask is, are there other, can we show a matching lower bound for other specific polynomials? Like one over x.
Yeah.
Or
not only for e to the power iht, but for other
specific polynomials. But if any generic method to implement polynomial transformations in this model would require omega of degree square, because for Hamiltonian simulation it requires omega.
Yeah, that's it.
Okay, any other question? Any question? Okay, I have a question. Go back. Yeah, so this method, this method, this randomized, you did not explicitly state the complexity of this method, right? You mention it in words, yes.
Like the depth is like theta tilde of d, which incorporates some d times log d, some log d, this kind of.
But what is, so for instance, you have a task here, right? Specific task. Go forward. Yeah, so this is the task that you want to implement, right? Right? So what is the circuit depth required to implement? Right, so there are two things: number of times you need to repeat the circuit and circuit depth of each run.
Yeah, if you are implementing like a polynomial transformation for degree t, then we need a like this same depth n. It has the depth n, which is slightly higher than n. Yeah.
But if you are interested in f of a instead of f of a,
then it will be d square.
Yeah. So basically,
because of this alpha coming in, we are not exactly implementing f of a, because there is an alpha factor, and alpha depends on d. So due to which, if you want to implement instead of f of a, then the depth again goes to d square, which again kind of matches the lower bound for Hamiltonian evolution.
And for
The main advantage is that we are reducing in the number of ancillas there. We are using only one ancilla.
and for linear systems, can you tell us the complexity, what we get? Remember that, or because that's a very cool application because it's capital M. Number of terms in the distribution of A.
Decomposition of A. Yeah, so L was coming just to have the construction of this unitary U using the block encoding.
There are no other questions. Let's thank the speaker once again. You can stop the recording. Stop sharing.